Welcome back to The Explainer. Okay, today we are diving into a paper by Kyle McLean-Smith, and I gotta tell you, it completely broke my brain in the absolute best way possible. We are going on an epic journey into the hidden geometric structure of physical space itself. So, get ready, because we're about to look at the very fabric of reality through a completely new and honestly fascinating lens.
So have you ever actually stopped to wonder, how does 2D space physically shrink? Like when we zoom way, way in, when a physical coordinate system contracts layer by layer down to the microscopic scale, what exactly is happening mathematically? It sounds incredibly complex, I know, but we're going to completely bypass all that dense jargon today and look directly at how physical space contracts, layer by layer, in a beautifully simple way.
All right, to really get this, we kind of need to look at the foundational math. Historically, we had some brilliant minds trying to map this out. Think Cayley-Farey with his fraction trees back in 1816, or Arthur Cayley mapping complex planes around 1846. They were trying to solve the incredibly tricky problem of how to cleanly represent this geometry. But this paper, it introduces this incredibly elegant modern breakthrough called side A normalization. Instead of using those messy complex maps, it just anchors the geometry by fixing the transverse base of a right triangle, side A, to exactly 1.
Let's translate this into something we can actually picture, like, say, the architecture of a building. This side A normalization basically anchors our horizontal x-axis to a unit base. Think of this x-axis ground as an unyielding horizontal floor. It's literally the physical foundation on which our entire geometric system rests. This floor is an absolute baseline, it doesn't shrink, and it definitely doesn't move. Which brings us to, honestly, the star of the show, the number 1. In this model, exponent 0, written as d to the power of 0, is exactly 1. And this isn't just some abstract mathematical idea, right? It's our absolute fixed anchor on the x-axis. Everything else is going to scale around this solid, unbreakable unit of 1.
So, if our horizontal floor is totally locked at 1, how on earth do things actually get smaller? Well, while the floor stays put, our y-axis acts a lot like a descending elevator. We measure linear lengths along this vertical y-axis to get what the paper calls our vertical height factors. As we step inward, nesting deeper and deeper into the geometry, this y-axis elevator contracts downwards, defining our one-dimensional height step by step. Okay, let's look at how this builds, because this is where the math gets absolutely mind-bending. Just look at this divergence. The one-dimensional vertical height, it contracts like normal steps. -1, +1, +2, +3. Just a simple sequential step down the elevator. But look at the 2D area exponents. They mysteriously leap strictly across odd integers, -1, +1, +3, +5. The even numbers are just, poof, gone. They are completely missing from the 2D spatial sequence.
What we're looking at here visually illustrates the golden decay sequence. It's literally a map of 2D space scaling inward across these nested geometric shapes, which the author calls cork tiles. We're going to zoom in and track this beautifully colorful progression, tile by tile, so we can figure out exactly why those spatial area exponents are skipping the even numbers entirely.
To make this super clear, we're going to break this inward spiral down into a really digestible 3-step progression. We'll start with step 1, the macro column, then we'll check out step 2, the first cork, and finally, step 3, the second cork. By tracking these 3 specific tiles, we're going to uncover exactly where the mathematical rules of physical space just completely shift gears as we zoom in.
All right, let's start with step 1, the macro column. This is denoted as tile D-1. You can think of this as our spatial expansion. Under golden ratio inputs, it scales outward with a value of phi, which is approximately 1.618. Try to picture this macro column as macroscopic space scaling outward, expanding way past our peripheral vision into this unknowable macro space.
Now things get super interesting at step 2, the first cork, or D0. This tile forms our perfectly clean primary baseline. Remember that unyielding x-axis ground of 1 we talked about? Well, the first cork sits exactly on that base, meaning it has a full unmodified transverse width of exactly 1. It experiences absolutely 0 width subtraction. Because only its height is contracted, its area gives us the pure golden ratio reciprocal, phi to the -1.
But hold on tight, because right here is where the sequence radically shifts. Step 3, the second cork. As that spiral turns inward to the next nested tile, a governance shadow is cast across the base. For the first time, the horizontal width is forced to contract. This dual contraction of both width and height triggers an exact cubic phase shift. The spatial area suddenly jumps straight to phi to the -3. And get this, the author actually identifies this exact specific mathematical jump as perfectly matching the metallurgical copper reciprocal. How wild is that?
So why exactly does the area just skip the even numbers? It's actually a really beautiful piece of logic. Let's trace it. The 1D height only contracts the vertical y-axis, so it counts linearly, right? 1, 2, 3. But 2D area is width times height. Because each new nested turn casts a shadow that shrinks both the width and the height simultaneously, those decay factors actually multiply together. That dual contraction is exactly what forces a mandatory +2 jump. And that is exactly why the spatial geometry skips the even numbers entirely and leaps across odd integers.
Wait a second, though. Let's really think about this for a minute. If our area exponents go from -1, jumping straight over to +1, then 3, then 5, what on earth happened to exponent 0? I mean, it is completely missing from that 2D area sequence. Where did it go?
Well, it turns out it didn't just disappear. Exponent 0, where d to the power of 0 equals 1, is acting as what the author calls the conjugate mirror pivot. It's sitting perfectly exactly between the -1 and the +1. It is the literal 0-point physical boundary that balances the massive macro expansion on one side and the zooming micro contraction on the other. It acts as a perfect geometric mirror.
And the coolest part is, we can literally prove it algebraically right here. If we take that expanding macrocolumn area, which is phi, and multiply it by the contracting first quark area, which is phi to the -1, they perfectly cancel each other out. The result is phi to the power of 0, which gives us a bold, undeniable 1. The expanding macrospace and the contracting microspace reflect perfectly across each other to equal exactly 1. So, why does this 0-point mirror matter so much in the grand scheme of things? Well, because it ensures the whole geometric sequence remains perfectly symmetric and completely balanced. You see, in traditional physics models, calculations can just infinitely drift smaller and smaller, until the math basically breaks down into infinities and requires all these messy corrections. But in this framework, the unyielding 0-point mirror locks the geometry into a perfectly balanced reflection. It halts that infinite drift completely.
Which leaves us with, honestly, a pretty profound question to ponder as we wrap up this explainer. If the foundational scaling of two-dimensional space is governed by this incredibly elegant, balanced reflection across a mathematical 0-point mirror, what other structures in the physical universe might be hiding on this exact same unyielding baseline? From quantum state machines to the very bounds of macroeconomics, if this geometry holds true, it fundamentally rewrites how we understand the architecture of reality. Thanks so much for exploring this with me today on The Explainer.